Problem number 6. Okay, so this is also hypothesis testing problem, but now we are not testing for mean or proportion. We are actually checking if the distribution in the categories is the same as expected. Okay. For example, so let us consider the example, and this is something similar to what you also need to do in the lab number 7. Okay, so the advisor of varsity sports team at a large university believes that the group consists of 10% freshmen, 20% sophomores, 40% juniors, and 30% seniors. The membership for team this year consisted of 14 freshmen, 19 sophomores, 51 juniors, and 16 seniors. At the significance level 0.1, test the advisor's claim. Okay, so this is the claim. H0 and H1 in this case are always the same. H0 is distribution is as we expected, 10%, 20%, 40%, 30% accordingly. And H1 is opposite. H1 is opposite, distribution is not as claimed in H0. So in this case, we are not going to use normal distribution or t-distribution. We are going to use the other distribution, which is called the chi-squared distribution. Yeah. And the test which we are going to run is called goodness of fit test. Okay, but the procedure is absolutely the same. So we are going to calculate test statistic. We are going to compare test statistic to the critical value, or we are going to calculate p-value and compare to the significance level. And then we will reject or accept H0 and accept or reject the claim. Okay. Okay, so in this case, this is our claim. This is H0. This is H1. The total number of the students is 14 plus 19 plus 51 plus 16. This is 100. So 100. So 100 students, this is our sample. And out of these 100 students, 14 are freshmen, 19 sophomores, 51 juniors, and 16 seniors. Okay. We need to calculate first our test statistics. So this is the formula for test statistic. O means observed frequency, E means expected frequency. Expected, that's what we have here, 10%, 20%, 40%, and 30%. So out of 100, which we sampled. Be careful, in this case, it's going to be 10, 20, 40, and 30, right? Because 10% from 100 is 10, 20% from 100 is 20, 40% from 100 is 40, and 30% from the 100 is 30. For the different number in the sample, it's going to be different, so be careful with this. So always calculate that. So always calculate those expected values. In this case, it's going to be quite straightforward, as I said. It's going to be 10, 20, 40, and 30. So that's what we expect. What we actually observe. So what we actually observe is what we have. What we have, that's 14, 19, 51, and 16. So let's put it here. 14, 19, 51, and 16. We can see right away that it's not going to work well, right? Because the only more or less matching number is here. Everything else is significantly different. But let's see. So we have our significance level given. So let's now quantify that result, because visually we can see that it's not the same. So it's not the same. So we are kind of visually can reject that claim. But again, guys, everything what we do, so must be proven. So we need to prove that. We need to present some quantitative estimation. So we need to prove that with some significance level. At some significance level. Okay, so the observed. So this is equal to observed minus expected squared. Okay, and so then we drop it down. Okay, so and then here we have this is equal to observed minus expected squared divided by expected. Okay, and then we double click here. Okay, and then we need to sum those numbers up. That's what this sigma capital means. We need to sum all those values. And this is going to be our test statistic chi squared. Yeah, so it's this value right there. So this is equal to sum, not sum. Yes, sum of these values right here. Okay, and this is our test statistic. And we need to compare the statistic to the critical value. Yeah, so in the critical value, we need to take 0.1. So this is inverted. We need to use inverted function. And as for the normal distribution and t-distribution, we also have a function for chi squared, like in Excel. Okay, so this is equal to. So this is also, by the way, right tail test. Yeah, so this is a right tail test. So this is just from the nature of the chi square distribution. So it has it has like this type of shape. So kind of this shape like this here. Okay, and there is no like left tail. Yeah, so there is only right tail there. Okay, here we have. Critical value, so the chi squared distribution, and we need to take inverted. So we need to take the area, inverted, right tail. Okay, inverted right tail, and probability 0.1. And degrees of freedom in this case, and in your problem in the lab number 7, as well as on the final exam, the degrees of freedom in this case is just the number of the categories. We have minus 1. This is like one-dimensional problem, and that's what it is in this particular case. In some other cases, it might be different, so problems could be much more complicated. It can be like two-dimensional problems. So in this case, we need like to set up those contingency tables and so on and so forth. But in this simple case, as well as on the final exam and in the lab number 7, so it's just the number of the categories minus 1. So it's 1, 2, 3, 4 in this case. 4 minus 1 is equal to 3. Okay, so this is our critical value. So this is our critical value. So you see it's a right tail. So it's right tail, so it takes the area in the right tail. You can also calculate it as inverted from 0.9, right? So if you take the chi squared distribution inverted from 0.9, and degrees of freedom is 3. We will see same value. See, it's the same value. You can use this function, or you can use that right tail. So then automatically it will understand that we want to find such a value which cuts a 0.1 like area on the right. Okay, or like it's 0.9 like to the left, right? So this function is counting like to the left. Okay. Okay, then as we can see, the critical value is less than the statistic. The statistic is in the critical region. That means we are making conclusion. Reject H0 and reject claim. Okay, so don't forget about conclusion. So that's the most important thing in all this procedure, because that is why like we are doing all this stuff, like to make that final conclusion. We can also calculate p-value. So p-value is Again, so that's the right tail. So that's the right tail. We need to find the area from the right, from this value. Yeah, so from this value. So always right tail test. So we can say that this is equal to the chi-squared distribution. So again, we can take a right tail right away, right tail. So we can take that value and degrees of freedom 3. Okay, so this is our p-value. As you can see, our p-value is significantly less than our significance level, and we make the same conclusion. We reject H0 and we reject the claim. Okay, so that's it. That's what you need to do, like in problem number 6 on the exam and in your last lab number 7.